Hey guys, in this video we're going to be talking about how to detect exoplanets. Alright, so in the last video we talked about what exoplanets are and why they're kind of important. Basically, they're planets that are in another solar system orbiting a different parent star, host star, whatever you want to call them. And they're important because they give us an opportunity to find planets that are potentially habitable. So the thing that's important about habitable planets is that it's twofold. So there are two reasons why it's important. The first one is probably one of the oldest questions humanity has had is, are we alone? Are we alone in the universe? Is Earth the only planet that supports life? And if you find a habitable planet that's already inhabited by something else, then that answers that age-old question, and it tells you once and for all, no, we're not alone. Now, if you don't find any living things on these exoplanets, that's not to say that there aren't living things on any exoplanets anywhere. We still won't know that for sure, but what it gives us the opportunity for is if Earth, for any reason, becomes uninhabitable. It will eventually, in the next couple billion years, the sun will heat up to the point that our habitable zone will move out past the orbit of Earth. So basically right now, the sun is here, the Earth is here, and the habitable zone is like this, and we're very comfortably inside it. But as the sun gets hotter, this region of space will be too hot to live in. And so the boundaries of the habitable zone will get pushed out, let's say there. And then Mars might become a habitable planet, and Earth would not. Too hot for liquid water. So now, one option if Mars becomes a habitable planet is for us to just jump from this planet to that one and start civilization all over again. But what about the end of the solar system? If humanity or our successors last long enough that they reach a point where the sun is about to die and all of these planets are about to be vaporized, what do? You need another planet on which you can live. Now, you could try one of the outer planets or the dwarf planets way out in the Kuiper Belt, but none of them seem like a really good fit. The outer planets and their moons, the outer planets themselves, there's no surface for you to stand on. Their moons might be a possibility if they aren't so freezing in a couple billion years. Way out in the Kuiper Belt might still be too far for it to be comfortable for us to live on. So one other option would be to find exoplanets out in another solar system around a star that has several billion years left in its life and might have liquid water on its surface. Then you just instead of hopping from planet to planet in our solar system, when our solar system is about to die, you hop from solar system to solar system and you go to a different one, a planet orbiting a different star to keep your civilization alive. So those are the two uses for finding planets that you could find life as we know it. It's not necessarily so that we find living things, it's also so that we find a second Earth, a second home, if we mess up this planet, which we kind of are. We're not that far away from kind of ruining Earth, and if we need another planet, we're going to need it probably fairly soon. But in this video, we're going to talk about how to detect exoplanets, and there are two techniques I want to talk about. The first one is called a Doppler Wobble. You could call it a Doppler shift or something, but I'm going to call it a Doppler Wobble. And the second one, sounds much fancier, is called transit photometry. Okay, so there are two things, and they're both quite different from one another, but they both depend on light. They depend on light in different ways, but they both depend on light. So the first one we're going to talk about is the Doppler Wobble. Now, you may recognize one of these, hopefully you've heard of the word wobble, but you may recognize this word from something else. You may not, but that's okay. There's something in physics called the Doppler shift. And you can experience this with waves. So you can experience this with light, you can experience this with sound, for instance. And basically what it is, so the Doppler shift, I'm going to erase transit photometry. You don't need to write down, I mean, you can write down what Doppler shift is, it's kind of useful. So Doppler shift is if you've got yourself over here as an observer, and you've got somebody else over here as another observer. So let's say you've got, you know, a light source or a boom box or whatever here in the middle, and it's moving that way. All right, so it's moving towards observer, I don't know, B for Bob. We'll call this one Bob. And we'll call this one Alice. All right, so our star or our boombox or whatever is moving towards Bob. Now, if it's a star and it's emitting light, when it's emitting light rays, it's emitting them, you know, with the same distance in between the waves in all directions. But if it's moving towards Bob, then the light rays that are being emitted in that direction are squished together because it emits a light ray, but then it moves a little bit and emits another light ray, and it moves a little bit and emits another light ray, and they end up actually being kind of squished together. So the light rays that are traveling towards Bob will be more squished together, and the light rays traveling towards Alice will be more spread out. Hopefully you can see the difference there. So if our star is moving in the direction of Bob, these light rays, because they're more squished together, they appear bluer. And this is called a blue shift. For Alice, it's on the other end of the rainbow. They look redder. So maybe the star itself is actually yellow, but when Bob takes a picture of it from one side, it looks blue. And when Alice takes a picture from the other side, it looks red. And this is called the Doppler shift. You can also experience this with sound, and you've all actually experienced it with sound. When you hear, let's say, one of the motos drive by on the street, you hear the pitch go from high to low as it passes you by. If they're playing music, you hear the pitch of the music change. All the notes go down, all the notes go flatter. And that's also because of the Doppler shift. As the moto is coming towards you, let's say the moto is coming towards Bob, all the sound waves are ever so slightly compressed closer together, and the pitch of the music is a little bit higher. So Bob hears it a little bit higher than the moto driver, and because it's moving away from Alice, the pitch is actually lower for Alice. So Alice hears it a little bit lower than Bob does. And if you have the moto pass you by, then as it's coming towards you, it's the waves are compressed closer together, so you hear it higher, 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 and then it passes you by, and all of a sudden the pitch drops way lower. So that's the Doppler shift, and basically the Doppler wobble takes advantage of this property of waves. And so basically what happens is, let's say you've got a star here and a planet here, a really heavy planet like Jupiter. So the planet is not simply orbiting the star. What's actually happening is the planet is orbiting a point in space, and the star is actually also orbiting a point in space. They're both orbiting the center of mass, let's say where this dot is, of the system. Well, actually, that's not where it would be right now. I've drawn this very poorly. Good gracious. All right, there's our star. There's our center of mass. All right, so it's the mass of the star and the planet sort of combined together. Where is the center of that mass? If you had a stick with the mass of the star on one side and the mass of the planet on the other side at each end, where would you have to hold your finger in the middle of that stick so that it balances? So it would be really close to the star, but it wouldn't be exactly where the center of the star is, because the planet is pulling on it. And so the star and the planet both orbit this point in the middle called the center of mass. So basically what happens is the planet does most of the motion because it's the smaller body and it's farther away. So it moves in a very drastic manner that you can see when you see planets orbiting the sun or the moon orbiting the Earth, all of that. But the star also orbits in this much, much smaller orbit. And so basically, if you watch it over time, it's just wobbling, sort of in a repetitive motion, in a predictable motion that you can calculate, but it's sort of wobbling around the center of the system. And the thing is, if you're over here on Earth, observing this system, when the star is moving this way towards that center of mass, it's moving towards you. And so the light waves that come towards you are more compressed, and it looks ever so slightly bluer. And then when the star is up here moving away from you, its light waves are slightly stretched out, and so to you it looks redder. Now if you observe the star over a period of months or years, sometimes even just days and weeks, then you'll notice that the star, in a very predictable manner, in a very periodic fashion, so every few days or every few months, you can predict that it'll look bluer and then maybe yellower and then redder, and yellower, bluer, yellower, redder. And if you notice that very, very precise pattern, you can assume it's because of a planet orbiting the star. Notice that you didn't actually see the planet directly. Just by the motion of the star, you can deduce, you can guess, you can understand that there must be something relatively massive orbiting the star. And that's the Doppler Wobble. Basically, you have a planet or some other heavy body, could be a bunch of planets, I don't know, orbiting the star that cause it to wobble in space. And that wobble translates to the star appearing ever so slightly bluer and ever so slightly redder to an observer on a planet in a different star system, stationary relative to this system. So that's the Doppler Wobble. The other thing was called transit photometry. And with a transit, once again, you don't necessarily see the planet itself. Now, what is a transit? A transit is basically when an object passes in front of a star or in front of another object. So in our solar system, if you're looking from Earth, and let's say this is the sun, you might see Venus just pop up as a small dot in front of the sun. And if you take pictures over the course of several hours, you'll see that Venus just moves across the surface of the sun as it's just moving in its orbit. So basically this is called the transit of Venus. You just see this little black shadow of Venus moving across the surface of the sun. Now, you could say that an eclipse is a type of transit. The moon is moving across the surface of the sun. The only catch is the thing that's transiting is the same size as the sun, so it covers the whole thing. But with a transit of something in a different solar system, when you've got stars which are really, really bright and they're off in the distance, so they look really small, and then you've got a planet transiting them, it's almost impossible to see the planet that's transiting. I'm drawing dots on the board, but I don't know if you can see them. This is basically what it's like when you're trying to observe a transit of a planet in a different solar system. So you don't try to take a picture and notice this black dot moving across the surface of the star. What you try to do instead is you take so you've got the star here and the planet is about to begin its transit, and what you do is you measure the light level of the star over time. So it's traveling through, your graph is going through time and you're measuring the brightness B of the star. All right, so you've got before the transit, during the transit, when this planet is, moving across the surface of the star, and then let me make it in kind of some separate drawings. So you've got the planet is starting its transit, the planet is ending its transit, and the transit is over. So you've got this planet that's just about to begin its transit, but it hasn't yet. So the brightness level of the star will be about at its maximum, we'll say 100%. But then the planet begins its transit. Now the brightness of the star won't drop by much, but the planet is blocking some of the light. So what happens is we notice a dip in the brightness, and that dip stays pretty constant because the size of the planet is constant. until the transit is over, when it goes back up to 100%. Now this dip is not going to be a very big one. This dip will maybe take it down to 99% or 99.5%. So basically what you see is when you finish making your measurements, all you do is you measure the brightness again, measure the brightness again, measure the brightness again, and you just keep draw a graph of what's the brightness of the star over the course of several hours or several days or whatever. And if you notice this periodic drop, now if it happens one time, it could be because of an asteroid or something, but if it happens in a very regular fashion, then you can figure out that there's a planet there. And basically, the idea is that, once again, without actually directly observing the planet, you can deduce that there is a planet orbiting that star. Now, there are systems in place that if you've got two planets orbiting, you can have this type of graph almost be overlapped by a similar type of graph for like the second planet, and it all gets very, very complicated very, very fast. But basically, the system can figure out, the computer programs and the astronomers can figure out if there's a planet transiting, how many there are, how big they are, how far away from the star they are. They can figure out all this different type of information just from this graph of a planet transiting its parent star. So in neither the Doppler Wobble nor transit photometry do you actually see the planet, but you can detect them. Now, just a final note for you to think about: for both the Doppler Wobble and the transit, for the Doppler Wobble you need the planet to be massive, you need it to be pretty big and pretty heavy, and for the transit you need it to be big enough that it blocks a substantial amount of light. So you can see that both of these techniques favor large planets, Jupiter-sized planets. They also favor shorter orbits. If you have to measure this dip, but you see it now, and then you see it in 15 years, and then you see it in another 15 years, you might not notice that it's actually traveling in a periodic fashion. Especially if you've only been observing things for 30 years, you might have seen this once, but then the planet still hasn't finished its orbit. So the reason you haven't seen a second transit is just because it's far away from its parent star. So in order to see this periodic graph multiple times, the orbit must be fairly short. And in order for it to be this pronounced, the planet has to be fairly large. And so that's why this technique and also the Doppler Wobble favor big planets orbiting relatively close to their parent stars. All right, I've gone a little bit over this time. Your next lesson will be a final exam breakdown and then a bit of a review. So I'll see you there.